So good afternoon, January the 26th, 2015. This is MATB110, Section 1, Calculus Point. Today is day number 7 into the semester, week number 4. So let's get started. Now, first of all, welcome back to this class. Remember, this is day number 7 into week number 4. And as I reminded you at the very beginning, if you read the teacher's message from last week, normally I delay my teacher's message for 1 week. So you can read that. We have a homework, which is assignment number 2 coming up. Again, it's due on Wednesday. You need to submit a hard copy to the TA and scan your homework into PDF and submit the PDF copy through the Moodle environment. One thing, may I remind you, based on my experience of reading your PDF last week, many of you scan one PDF per question. So I have many PDF of your submitted account. But what I expect is you just scan all your homework problem into one PDF so that I do not need to download so many PDF to read one student's work. Okay? So make sure this time, do not give me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 PDF per student. That is a lot of work for me to download your PDF document. So please help, okay? When you have finished all of these, okay, scan them once into one PDF. So I have one PDF file per student, okay? Help me, all right? So the second thing I need to remind you is, this Wednesday, you're going to receive the graded homework from last week, and so you also need to scan your graded homework and submit the graded homework PDF to the system. I will show you the link minutes later. So make sure, again, one PDF for the whole graded homework, okay? So do not make my life difficult, all right? So the second thing you need to know is you have a quiz coming up this Wednesday during tutorial, which is based on 2.2 and 2.3 of the textbook. If you have a textbook or a copy of the textbook, turn to 2.2 and 2.3 and you will know what the two sections are all about, okay? And very conscientious students have already indicated it's about limits and more about limits, okay? And remember, I just want you to hear loud and clear, the best way to prepare for your quiz is to make sure you do the exercise, which is suggested as homework, and also 1 or 2 questions in the cluster of your homework problem. It should not be more or less the same. The practice just to make sure that you have enough of the understanding, okay? So, I have given you some informations, and the quiz, I will actually send the question to the TA, and the TA will come here, not to distribute your paper, but he will use the projector, project on the screen, and you can see the questions on the screen, and you do the questions using your own paper, okay? And so, make sure you write the name and student ID on that piece of paper. As many pages you want, keep the page number and send it to the TA at the end of the quiz. So please make sure you go through the very simple instructions here. I just want to make sure you know the housekeeping. Alright, now let me go back to the week's reading. So basically, I want you to be aware of studying from week number 2. We have already put into practice the specific learning mode that you need to be operating on. Before class, you click on the link here, you know there's something I expect you to complete it before you come to class. And during class, it's basically something you know that at the end of the class exercise, you can come back here to review what we have gone through. After class exercise is also very important because it will give you a very concise summary of what we have gone through together with the notes I expect you to read. And with exercise, it's basically something I want to remind you to get prepared before the coming of the next week. So, starting on week number 2, you should have already gone through some exercise, and I see these called come along exercise with me. Okay, so now let's go to the reading for week number 2 to get to review. So So reading for week number 2, basically start with chapter 2, is where your quiz is going to be all about. This is 2.2, the limit concept, and this is 2.3, more about limits. So you can take it at a glance what your textbook has been doing for you, and you can compare this with the exercise you have done, okay? So, and then, at the end of each reading list, I've also given you some help in order to make sure that if you need some extra help, those intellect resources will help you. And these resources will also be able to help you to complete the notes. Do you remember how many times you need to submit the notes in order to earn how many percent of the semester grade? 15, okay? 4 times. When is the first time coming, okay? So check on the teacher's message of last week. So this is the reading for week number 2, and the reading for week number 3 comes here. So last week, the reading list comes on chapter 3, the derivative. I've actually given you the topics and the page number. And so you can take a look at the way your textbook has been structured and help you learn something very specific in the derivative. And today, we are going to come down to some of those very specific things, okay? Using the MIT OCW core structure to match what you need to learn. And we are relying a lot on the help of one, Professor Gilbert Strand, giving you height-wise of the calculus. 2, Professor David Jerrison's giving you the specifics on the proof, on the workout, and also if you look at the specific before class activity, ever since last week, do not forget the recitation section, which is just like a tutorial, okay? So let me bring you to the reading for this week, which is week number 4. Now, every reading is basically taken out directly from your textbook. So this week, the reading comes directly from the second half of chapter 3, okay? And today, our focus is on the first one, the derivative of sine and cosine, okay? All right, a lot of you have already asked me questions ever since the second week, and I say, please be patient, we'll come to that. If not, on the third week, this week at the beginning. So, very important. And then take a look at the differentiations concept, okay? These will help you to come up with some denotes and differentiations. And again, rates of change. Now, what do we mean by rate of change? Okay, in context of differential calculus. Now, we have already got the ideas that in differential calculus, we're interested in, number 1, the geometric interpretations of differential calculus. What is meant by the geometric interpretations of differential calculus? We're interested in working on the slope functions, okay, of a tangent line to a particular curve at a particular point, all right? And that is called the geometric interpretations. When we talk about the rate of change, that is the physical interpretations, okay? That is the physical interpretations. Okay, let's go back to the course website, and this is week number 4, okay? Week number 4, now let's come to before class. And I hope that you have been making the best use of these resources, okay? I have invited you to take a good look at these 2 videos. Actually, ever since the first week, I invite you to take a look at it. And we will come to that. This is sections 3.5 of the chapter. We'll hold this, okay? But we will introduce to you, first of all, some very good resources provided by Professor Gilbert Strand. So far, up to this week, we would like to start exploring chapter 3, the applications of derivative. So this is where we are. And we're going to talk something more about this today using Professor David Jerrison's help, okay? And then, towards the end, on task number 2, I have given you some very important tutorial video, even though you didn't have a chance to ask questions during your tutorial sections. All of these are given in context of short, up-to-the-point video 5 minutes, 7 minutes, 10 minutes proposed to help you to remember, to understand all of these very important contacts. Now, if you're ready, do not forget, so far we are walking into this course, okay, based on your textbook, using the resources of OCW from MIT. Now, studying this week, I want to emphasize that it's time for you not just to read your textbook, not just to do your exercise, but to make sure you make the best use of what we call the recitations resources. These are recitations resources where you can watch a TA solving problems for your understanding. Okay? Normally when we provide tutorial, we provide the chance for you to watch someone solve problems of that particular concept for you. And so far, the important thing is you must understand this, you must understand that, you understand something like this, and we will provide continuous resources on this side. Spend some time, particularly during the weekend, to watch some of those workout problems, okay? Okay, now let's go back to a specific lecture. Today, we're coming back to David Joseph's with the specific lectures here. So please pay attention on the derivative of sine and cosine. Okay.
The following content is provided under affiliated public license. Your support will help MIT Open Courseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT Open Courseware at www.mit.edu.
Derivative of the sine.
Today's lecture I want to develop several more formulas that will allow us to reach our goal of differentiating everything. So these are derivative formulas. And they come in two flavors. The first kind is specific. So some specific function we're given the derivative of, and that would be, for example, x to the n, 1 over x, those are ones that we did a couple of lectures ago. And then there are general formulas, and the general ones don't actually give you a formula for a specific function, but tell you something like, if you take two functions and add them together, their derivative is the sum of the derivatives. Or if you multiply by a constant, for example, so c times u, the derivative of that is c times u prime, where c is constant. Alright, so these kinds of formulas are very useful, both specific and general kind. For example, they're needed, so we need both times. For polynomial too. And more generally, pretty much any set of formulas that will give you a few functions to start out with, and then you'll be able to generate lots more by these general formulas. So today, we want to concentrate on trig functions, and so we have some. We'll start out with some specific formulas. And they're going to be the formulas for the derivative of the sine function and the cosine function. So that's what we'll spend the first part of the lecture on, and at the same time, I hope to get you very used to dealing with trig functions, although that's something that you should think of as a gradual process. All right, so in order to calculate these, I'm going to start over here and just start the calculation. So here we go. Let's check what happens with the sine function. So I take sine x plus delta x, I subtract sine x, and I divide by physical space there. Sine x and divide by delta x. All right, so this is the difference quotient. And eventually I'm going to have to take the limit as delta x goes to 0. And there's really only one thing we can do with this to simplify or change it, and that is to use the sum formula for the sine function. So that's this, that's sine x cosine delta x plus that's not what it is. Okay. So what is it? Sine x sine delta x. Okay, good. Plus cosine. No. Oh, okay. So which is it? Okay. All right, let's take a vote. Is it sine sine or is it sine cosine?
Sine cosine.
Okay. So is this going to be
Cosine.
cosine? All right. All right, you got to remember these formulas, all right?
These are secondary school.
Okay, it turns out that it's sine cosine. All right, cosine. So here we go. No, we got to do x here. Sine cosine. All right? So now, there's lots of places to get confused here. You're going to need to make sure you get it right, all right? So we're going to put those in parentheses here. Sine A plus B is sine A cos B plus cos A sine B. All right? Now that's what I did over here, except it was the letter X was A and the letter B is delta X. Right, now that's just the first part. It's just this part of the expression. I still have to remember the minus sine x. That comes with the minus sine. And then I have to remember the denominator, which is delta x. Okay? All right, so now, the next thing we're going to do is we're going to try to group the terms. And the difficulty with all such arguments is the following one. Any tricky limit is basically 0 over 0 when you set delta x equals 0. If I set delta x equals 0, this is sine x minus sine x, so it's a 0 over 0 term. Here we have various things which are 0 and various things which are non-zero. We must group the terms so that a 0 stays over a 0. Otherwise, we're going to have no hope. If we get some 1 over 0 term, we'll get something meaningless in the limit. So I claim that the right thing to do here is to notice, I'll just point out this one thing, is that when delta x goes to 0, this cosine of 0 is 1. So it doesn't cancel unless you throw in this extra sign. So I'm going to use this common factor to combine those terms. This is really the only thing that we're going to have to check in this particular calculation. So we have the common factor sine x, and then that multiplies something that will cancel, which is cosine delta x minus 1 divided by delta x. That's the first term. And now what's left? Well, there's a cosine x that factors out, and then the other factor is sine delta x. Okay, now, does anyone remember from last time what this thing was? How many people say 1? How many people say 0? All right, it's 0. That's my favorite number. All right, 0. It's the easiest number to deal with. So this goes to 0. And that's what happens as delta x tends to 0. Now how about this one? This one goes to 1. The second favorite number. Almost as easy to deal with as 0. And these things are picked for a reason. They're the simplest numbers to deal with. So altogether, this thing, as delta x goes to 0, goes to what? I want a single person. Grade on. All right, like that. Cosine. Because this factor of 0 cancels, and this factor has a 1, but it's cosine. So it's cosine x. All right, so our conclusion over here, with orange, is that the derivative of the sine is the cosine. Okay, now I still want to label these very important limit facts here. This one we'll call A, and this one we're going to call B, because we haven't checked them yet. I promised you I would do that, and I'll have to do that this time. So we're relying on those things to be true. Now I'm going to do the same thing with the cosine function, except in order to do it, I'm going to have to remember the sum rule for cosine. So we're going to do almost the same calculation here, and you see that will work out. But now we have to remember that cosine of A plus B is equal to cosine cosine. No, it's not cosine squared because there are two different quantities. Cosine A, cosine B, minus, here's the minus sign, sine A, sine A. All right. So you'll have to be willing to call those forth at will right now. So, okay, so let's do the cosine. So that's cosine x plus delta x minus cosine x divided by delta x. Okay, this is this quotient, the cosine function. And now I'm going to do the same thing I did before, except I'm going to apply the second rule, that is the sum rule for cosine. And that's going to give me cosine x, cosine delta x, minus sine x sine delta x, and I have to remember again to subtract cosine divided by this delta x. And now I'm going to regroup just the way I did before, and I get the common factor of cosine multiplying cosine delta x minus 1 divided by delta x. And here I get the sine x, but actually it's minus sine x. And then I have sine delta x. All right? The only difference is this minus sign. This side. So that's not the only difference. It's the crucial difference. Okay, again, by A, we get that this is 0. This delta x tends to 0. This is 1. This is the properties I call A and B. And so the result here, as delta x tends to 0, is that we get negative sine x. So this guy is negative sine x. I'll put a little box on it. All right. Now, these formulas take a little bit of getting used to, and but before I do that, I'm going to explain to you the proofs of A and B. All right, so we'll get ourselves started by mentioning that. Now, maybe before I do that, though, I want to show you how A and B fit into the proofs of these theorems. So,
it's very important to pay attention to the proofs.
So this is just a remark, but it's meant to help you to frame how these proofs work. So first of all, I want to point out that if you take the rate of change of sine x, so let's start first. It's actually a little bit less obvious. If I take the rate of change of cosine x, in other words, this derivative, at x equals 0, then by definition, this is a certain limit as delta x goes to 0. So which one is it? Well, I have to evaluate cosine at 0 plus delta x, that's just delta x. And I have to subtract cosine from 0, that's the base point, but that's just 1. And then I have to divide by delta x. And lo and behold, you can see that this is exactly the limit that we had over there. This is the one that we know is 0 by what we call property A. Similarly, if I take the derivative of sine x, at x equals 0, then that's going to be the limit as delta x goes to 0 of sine delta x over delta x. And that's because I should be subtracting sine of 0, and sine of 0 is 0. Right? So this is going to be 1 by our property b. And so the remark that I want to make, in addition to this, is something about the structure of these two proofs, which is the derivative of sine and cosine at x equals 0 if all values of united x sines. So that's really what this argument is showing us, is that we just need one way to change it one place and then work out all the rest of it. So that's really the substance of this proof. That, so of course, really then shows that it boils down to showing what this rate of change is in these two cases. So now there's enough suspense that we want to make sure that we know that those answers are correct. Okay, so let's demonstrate both of them. I'll start with B. So I need to figure out property B. Now, we only have one alternative as to a type of proof that we can get with this kind of result. And that's because we only have one way of describing sine and cosine functions. That is geometrical. So we have to give a geometric proof. And to write down a geometric proof, we have to draw a picture. And the first step in the proof really is to replace this variable delta x, which is going to 0, with another name which is suggestive of what we're going to do, which is the letter theta, for an angle. Okay, so let's draw a picture of what it is that we're going to do. There's a circle, and here is the origin, and here's some little angle. Well, I'll draw a little larger. Here's theta. And this is the unit circle. I won't write that down. That's the unit circle. And now sine theta is this vertical distance that we're going to draw in different colors. Let's see. Here's this distance. So this distance is sine theta. Okay? Now, almost the only other thing we have to write down in this picture to have it work out is we have to recognize that when theta is the angle, that's also the arc length of this piece of the circle when we measure the radius. So this length here is also arc length. What's arc length? Okay, that little piece of it. So maybe I'll use a different color for that. So this orange. So those are the two pieces. Now, in order to persuade you now that the limit is what it's supposed to be, I'm going to extend the picture just a little bit. I'm going to double it, just for my own linguistic sake, so that I can tell you a story. All right? So that you remember this. So I'm going to take theta angle below, and I'll have another copy of the sine theta down here. And now the total picture is really like a bow and bowstring. All right? So what we have here is a length of 2 sine theta, so maybe I'll look this way. 2 sine theta, I just doubled it. And here I have underneath I got it backwards. Sorry about that. Trying to be fancy with the colored chalk, and I have it reversed here. So this is not 2 sine theta. 2 sine theta is the vertical, that's the green. So let's try that again. This is 2 sine theta. And then in the denominator, I have the arc length, which is theta is the first half. So double it, it's 2. Right? So if you like, this is the bow. And up here, we have the bow string. And of course, we can cancel the 2's, that's equal to sine theta divided by theta. And so now why is this 10 to 1 as theta goes to 0? Well, it's because as the angle theta gets very small, this curved piece looks more and more like a straight line, right? And if you get very, very close here, the green segment and the orange segment will just merge. They will be practically on top of each other. And you have closer and closer and closer to the same length. So that's why this is true. I guess I'll articulate that by saying that short curves are nearly strict. Right? So that's the principle that we use. The short pieces of curves are nearly strict. Short pieces. All right, so now I also need to give you the proof of A. And that has to do with this cosine function here. This is the property A. And so I'm going to do this by flipping it around because it turns out that this numerator is a negative number. If I want to interpret it as a length, I'm going to want positive quantity. So I'm going to write down 1 minus cosine theta here, and then I'm going to divide by theta. Right? Again, I'm going to make some kind of interpretation. Now this time, I'm going to draw the same sort of bow and arrow arrangement, but maybe I'll exaggerate it a little bit. So here's the vertex of the sector, but we'll maybe make it a little longer. All right, so here it is, and here was that middle line, which was the whoops. Okay, we have to check it out. Let's try to do it. All right. Well, on your pencil and paper, it'll look better than it does on my glass. Okay, so here we are. Here's this shape. Now, this angle is supposed to be theta, and this angle is another theta. So here we have a length, which is again theta, another length, which is theta over here. That's the same as in the other picture, except we've exaggerated it here. And now we have this vertical line, which again I'm going to draw the green poster. But notice that as the vertex gets farther and farther away, the curved line gets closer and closer to being a vertical line. That's sort of the flip side by expansion of the zoom in principle. The principle that the curves are going to go straight and you zoom in. So if you zoom out, that would mean sending this vertex way, way out. The curved line, the piece of the circle, gets more and more strict. And now let me show you where this numerator, 1 minus cosine theta, is on this picture. So where is it? Well, this whole distance is 1, but the distance from the vertex to the green is cosine of theta. Right? Because this is theta, so dropping down the perpendicular, this distance down back to the origin of this cosine theta. So this little tiny bitty segment here, which is basically the gap between the curve and vertical segment. So the gap is equal to 1 minus cosine. Right? And so now you can see that as this point gets farther away, if this got sent off to the status center, you would probably be able to tell the difference. The bowstring would coincide with the bow, and this little gap between the bowstring and the bow would be tending to 0. And that's the stage point. This tends to 0. Scale. Yeah. Question. The question is, doesn't the denominator also tend to 0? And the answer is yes. In my strange analogy here with zooming in, what I did was I zoomed out the picture. So in other words, if you imagine, you're taking this, you're putting it under a microscope, and you're looking at something where the theta is getting smaller and smaller and smaller and smaller. All right? But now, because I want my picture, I extend my picture. So the ratio is the thing that's preserved. So if I make it so that this gap is coming, let me say this one more time. I'm afraid I've made life complicated for myself. If I simply let this theta tend into 0, that would be the same effect as making this closer and closer and then the vertical would approach. But I want to keep on blowing up the picture so that I can see this between the vertical and the curve. So that's very much like in our video screen, you zoom in, zoom in, zoom in, zoom in. So the question is, what would that look like? That has the same effect as sending this point out farther and farther in that direction, to the left. And so I'm just trying to visualize it for you by leaving the theta at the scale, but actually the scale of the picture is very changing. So both theta is going to 0, but I'm rescaling so it's of the size that we can look at. Watch, imagine what's happening. Okay, does that answer your question?
That seems to prove that that limit is equal to 0 over 0.
It proves more than it's equal to 0 over 0. It's the ratio of this little short thing to this longer. And this is getting much, much shorter than this total length. You're absolutely right. We're comparing two quantities which are going to 0. But one of them is much smaller. In the other case, we compare two quantities which are both going to 0, but they both end up being about equal. But here, the previous one was this green one. Here it's this little tiny bit. And it's way shorter than the two theta distance. Yeah, another question.
Cos theta minus 1 or cos theta is equal to 1 minus
Cos theta minus 1 over. So here, what I wrote is cosine delta x minus 1 divided by delta x. Okay? And I claim that it goes to 0. Here, I wrote the minus that. That is cosine theta. I replaced theta by delta x by theta. Then I wrote this thing. So cosine minus theta minus 1 is the negative of this. Right? And if I show that this goes to 0, it's the same as showing the other side. Another question. So the question is, what about this business about arc length? So the word arc length, that shape, that orange shape is an arc. And we're just talking about the length of that arc. And so we're calling it arc length. That's what the word arc length means. It just means the length of the arc. Why is this length theta? Okay, so this is a very important point. In fact, it's the very next point that I wanted to make. Namely, notice that in this calculation, it is very important that we use length. And that means that the way that we're measuring theta is in what are known as radians.
That was a very important point.
Right? So that applies to both B and A. It's a scale change in A and doesn't really matter, but in B is very important. The only way that this orange line is comparable to this green line, the vertical responsible to the arc, is if we measure them in terms of the same notion of length. If we measure them in degrees, for example, it would be completely wrong. We divide up the angles into 360 degrees, and that's the wrong unit of measure. The correct measure is the length along the unit circle, which is the radians are. And so this is only true here if we use radians. So again, a little warning here that this is in radians.
It's X in radians.
Here, X is in radians. The formulas are just wrong if you use radians. Okay, so the second question is, why is this crazy length here 1? And the reason is that what I did was, the relationship between this picture up here and this picture down here is that I'm drawing a different shape. Namely, what I'm really imagining here is a much, much smaller theta. Okay? And then I'm blowing that up in scale. So this scale of this picture down here is very different from the scale of the picture up here. And if the angle is very, very, very small, then 1 has to be very, very long for me to finish the circle. So in other words, this length is 1 because that's what I'm insisting. So I'm finding that that's how I define this circle. Another question. Okay, so the question is, it's hard to visualize this fact. Okay, so let me take you through a couple of steps, all right? Because I think probably other people are also having trouble with this visualization. The first part of the visualization I'm going to try to demonstrate on this picture up here. The first part of the visualization is that I should think of the beak of a bird closing down, getting narrower and narrower. So in other words, theta has to be getting, the angle theta has to be getting smaller and smaller and smaller. So that's the first step. So that's the process that we're talking about. Now, in order to draw that, once theta gets incredibly narrow, in order to depict that, I have to blow the whole picture back up in order to be able to see it, otherwise it just disappears on me. In fact, in the limit, theta equals 0 is meaningless. It's just a flat line. That's the whole problem with these tricky limits, is they're meaningless right at the 0 level. It's only just a little away that are actually useful. We can get useful geometric information out of it. So we're just a little away. So that's what this picture down below, part A, is meant to do. It's supposed to be that the theta is only a tiny cloud, just a little bit. And the smallest I can draw on the board to visualize is using the whole length of the black for that. So I've opened a little tiny bit, and by the time it gets to the other end of the black, it's really wide. But this angle theta is a very narrow, it's very small. Right? So I'm trying to imagine what happens when this collapses. Okay? Now, when I imagine that, I have to imagine a geometric interpretation of both the numerator and the denominator of this quantity theta. And just see what happens. Now, I'm playing the numerator is this little tiny bit of here. And the denominator is actually half of this whole length here. The factor of 2 doesn't matter when you're seeing whether something tends to 0. Right? And I claim that this here, because it's clear that this is much shorter than that vertical curve. And I'm claiming, so this is what you have to imagine, is that as it gets smaller and smaller and smaller still, that has the same effect of this thing going way, way, way farther away from this vertical curve getting closer and closer and closer to the beginning. And so the gap between them gets tiny and goes to 0. All right? So not only does it go to 0, that's not enough for us, but it also goes to 0 faster than the theta goes to 0. And that's what's over. I hope the evidence is pretty strong here in such times all over this. All right. We are going to move forward, and we'll have to ponder these things some other time. So I'm going to give you an even harder thing to visualize now, so keep it clear. Okay? Okay. So now, the next thing that I'd like to do is to give you a second proof, because it really is important, I think, to understand this particular fact more thoroughly, and also to get a lot of practice with sines and cosines. So we're going to give you, I'm going to give you a geometric proof of the formula of the derivatives. So here we go. This is a geometric proof. Of this fact, this is for all theta. All right, so far we only did it for theta equals 0. And now we're going to do it for all theta. This is a different proof, but it uses exactly the same principles. So I want you to do this by drawing another picture. And the picture is going to describe y, which is sine theta, which is the vertical position of some circular motion. So I'm imagining that something is going around in a circle, and some particles going around in a circle. And so here's the circle, here's the origin, this is the unit distance, and right now it happens to be at this location P. And here's the angle theta. All right, and now we're going to move it. We're going to vary theta. And we're interested in the rate of change of y. So y is the height of P. So we're going to move it to another location. We'll move it along the circle to P. All right, so here it is. Okay, so how far did we move it? Well, we moved it by an angle delta theta. We started theta, theta is going to be fixed in this argument, and we move a little bit delta theta. And now we're just going to try to figure out how far we can move. Well, in order to do that, we've got to keep track of the height, the vertical displacement here. So we're going to draw this right angle here. This is the position R. And then this distance here is the change in y. Right? So the picture is we have something moving around a unit circle, point moving around a unit circle. It starts at P and moves to Q. It moves from angle theta plus delta theta. And the issue is, how much does y move? And the formula for y is sine theta. That's telling us the rate of change of sine theta. Well, so let's just try to think a little bit about what this is. So first of all, I've already said this, I'm going to repeat it. Delta y is PR. It's going from P and going straight up to R. That's how far y moves. That's what I said on the right hand corner. Oops, I said PR, but I wrote PQ. Alright? Alright, so delta y is PR. And now, I want to draw the diagram again. So here's Q, here's R, here's P. And here's my triangle. And now, what I'd like to do is draw this curve here, which is the piece of the arc, the circle. But really, what I want to keep in mind is something that I did also in all these other arguments, which is, maybe I should have called this orange, but I'm going to think of this straight line. So it's the straight line approximation to the curve that we're always interested in. So the straight line is much simpler because then we just have a triangle here, and in fact, it's a right triangle. So we have the geometry of the right triangle, which is going to now let us do all of our calculations. Okay, so now the key step is this same principle that we already used, which is that short pieces of curves are nearly straight. So that means that this piece of the circular arc here from P to Q is practically the same as a straight segment from P to Q. Alright, so that's this principle that let's put it over here, is that PQ is practically the same as a straight segment. So how are we going to use that? Well, we want to use that quantitatively in the following way. What we want to notice is that the distance from P to Q is approximately delta K. Right? Because the arc length along that curve, the length of the curve is delta K, so the length of the green, which is PQ, is almost delta. So this is essentially delta K. This distance. Now, the second step, which is a little trickier, is that we have to work out what this angle is. So our goal, I'm going to put it one step below this and put the geometric reasoning in between, is I need to figure out what the angle QPR is. If I can figure out what this angle is, then I'll be able to figure out what this vertical distance is, because I'll know the hypotenuse and I'll know the angle, so I'll be able to figure out what the side of the triangle is. So now, let me show you why that's possible to do. So in order to do that, first of all, I'm going to straighten the boards and show you where the line PQ is. The line PQ is here. That's the whole thing. And the key point about this line that I need you to realize is that it's practically perpendicular. It's almost perpendicular to this ray here. Right? It's not quite because the distance between P and Q is not zero. So it's a part of the limit, it's going to be perpendicular. Exactly perpendicular. Tangent on the circle. So the key thing that I'm going to use is that PQ is almost perpendicular to OP. Alright, the ray from the origin is basically perpendicular to that green line. And then the second thing I'm going to use is something that's obvious, which is that PR is vertical. Okay? So those are the two pieces of geometry that I need to see. And now notice what's happening upstairs on the picture here in the upper right. What I have is the angle theta is the angle between the horizontal and OP. That's the angle theta. If I rotate it by 90 degrees, the horizontal becomes vertical, it becomes PR, and the other thing rotated by 90 degrees becomes the green line. So the angle that I'm talking about, I get by taking this guy and degrees, it's the same angle. So that means that this angle here is essentially theta. Let me repeat that one more time. We started out with an angle that looks like this, which is the horizontal, that's the origin, we got horizontal, that's considered 1. That is considered. Okay? I also have that's my right arm, which is 1. My left arm is pointing up, and it's going from the origin to the point P. So here's the horizontal, and the angle between these is theta. And now, what I claim is that if I rotate by 90 degrees up, like this, without changing, so that was what I did, the horizontal will become a vertical. That's PR, that's going up. And if I rotate OP 90 degrees, that's exactly PQ. Okay? So let me draw it on there one time. Let's do this arrow scoop. So I started out with this, and then we'll label this as, let's see, orange. Okay, so red to orange, and then I rotate by 90 degrees, and the red becomes this, starting from P. And the orange rotates around 90 degrees and becomes this. Right? So this angle here is the same as the other one. Different coordinates, different vertices. Okay? Well, I didn't say that all I'll use it. Alright, so I claim that the conclusion is that this angle is approximately theta. And now we can finish our calculation, because we have something with the hypotenuse being delta theta, the angle being theta, and so this segment here, PR, is approximately the hypotenuse length times the cosine of the angle. Okay? And that is exactly what we want. We divide by delta theta, we get delta y divided by delta theta is approximately cosine theta. And that's the same thing. So what we want to eliminate is exactly the delta theta.
We are not going to take attendance today because of time, so we'll let you finish the 2 minutes at home. Make sure you review the before class activity for this week number 4. And study section 317 of your textbook to review some of the missing points here. Thank you very much for coming.
That's it for today's MATB110 Section 1 Calculus 1 on January the 26th, 2015. Okay, until this first day, stay in tune.